first off, hey everybody, welcome. This is going to be what we were referring to as the top shelf, where we get some pretty high impact guests to come on and kind of talk about what they've done. And we're hoping to get some pretty unique angles to what we're asking and what we're doing. And today we have on here Chris Lattner. You might be probably one of the most influential engineers, I think, of our time. The things that you've written affect millions of people directly and indirectly, potentially most people on Earth. I would say that Clang and LLVM play a huge role in affecting people's everyday lives, whether they realize it or not. And also, you've written Swift, and now you're working on Mojo as kind of like the big highlights of everything you've done. Pretty impressive. Yep. You have a PhD, which is already more impressive than most people in chat. They can't even believe PhDs actually exist, so very impressive.
I think chat's most surprised you have a PhD and you're not like still writing Haskell. I think that's what chat considers one of your crowning achievements.
Yeah, I wasn't. I mean, I had a great time in graduate school. I wasn't actually a great graduate student. Writing the papers and being the academic was not my thing, but it was really amazing to get paid to work on the stuff that I wanted to build. So
okay, when you said you weren't good at being an academic, how do you get a PhD? How do you want to subject yourself to that many years of school but not being good at it?
I didn't. So I went to Illinois with the goal of getting in and out in a year with a master's degree. And then my advisor, Vikram, nerd sniped me and started working on this LLVM thing. And that became really cool. And I was having fun. And then I decided not to leave. So it's all his fault.
Dang. That's actually, nerd sniping is an extremely powerful technique. And I realize that you can solve a lot of problems by getting somebody else excited about what you're doing.
Yeah, well, so I mean, I think that something that defines what I work on is that I work on it both because I, intellectually care about achieving a thing, but also because I just fall in love with the problem and I get really excited about it. It's the enthusiasm that drives it. It's not just the rational, this needs to be solved in this way for whatever reason. I also love the process of discovery. And so being able to work through something and really understand it because you build into this the space really gives you a hands-on way to understand and build things. And I'm very fortunate that some of it was useful to other people too, and that's pretty cool.
I do like this little bit of history that I didn't know, that it was LLVM is just the world's longest and largest nerd snipe that's ever happened. Like, I really like this little tidbit now.
Yeah, well, I mean, it's super funny, right? I mean, you were talking about Rust. When we did the Mojo's faster than Rust blog post, a lot of people were saying like, "Oh my God, this can't be true. Rust has tail calls, and it'll even turn tail recursive functions into for loops, things like this, right?" And the thing that I think I'm pretty sure that 99% of people don't know, or certainly the people that are commenting don't understand, is that Rust does tail recursive for loop elimination nonsense because a university student, literally 21 years ago, got an idea for an algorithm implemented into LLVM, and now here you go. Rust can do this thing. And so you can go look at tail recursive elimination. If you go all the way back 21 years in history, you can see me hacking away, having fun, learning how this little algorithm works. And now it's a cool thing that Rust and Swift and Julia and Clang and like all this universe of languages can now all just get for free, which is pretty cool.
So what you're trying to say is you are one of the top contributors to Rust and its performance.
Actually, that would be really interesting. I am still by far the top contributor to LLVM, including all of its subprojects. I haven't done that cross comparison with Rust. I mean, you can go look at my GitHub profile on github.com/Lattner. And so like, I'm still writing some code and doing some useful stuff, but I haven't done that cross comparison to Rust or other communities. That's very interesting.
All right, so we are going to kind of go back and forth on some questions, and we're going to let TJ kind of start us off.
Yeah. So one of the things that I'm kind of interested in as someone who loves some not as popular languages is when you started working on Swift at Apple, one of the things you had said is that there were still a lot of people who loved Objective-C. So from sort of like almost like the human side of the problem, the structural side of the problem, what were some of the things that you did to deal with hesitancy? I mean, obviously for Swift, it's even bigger than a lot of the kinds of introducing new technologies because, you had to write an entirely new language. But there was lots of people at Apple who were like, oh, I've been writing Objective-C for, I don't know, longer than I've been alive. Wait, why do we need this new thing, right? So like, how did you tackle that inside of Apple?
Yeah, so great question. Let me just give you some factoids on that. So I started working on Swift in 2010. It was a nights and weekends project. 2014, it launched publicly to the world, and it got open source in 2016. Right? So you're talking about just that 6-year time frame. By the time it launched, 4 years into its journey, only about 250 people knew about it at Apple. Okay, and this is because of Apple's secrecy and like all the things that Apple is both notorious for and also wonderful at. And so one of the big questions I think you're getting at is like, how do you actually go from like a crazy idea to something that launches publicly to the world and now millions of people use, right? And so in the case of Swift, it was literally nights and weekends project that nobody at Apple even knew about except for me for a year and a half. So that 4 years, a year and a half of it was just me working on a thing to understand it, to explain. I had a day job running several really big teams, and so it was a relief valve after getting C++ to work in Clang and get the compiler to bootstrap and build Boost and like all these. C++ is a very formidable language to implement, and so you can't come out of that without some PTSD. And so Swift was kind of a release valve. Um, by the time it got interesting, and I was trying to understand it because again, I have to build things to really understand it. Then I said, "Hey, management, what do you think about this project?" Right, and the plus one Apple, I had built up enough credibility for delivering things that they didn't immediately say, "Go away, kid! Like you're not gonna like this is dumb." They kind of said, "Well, that's very interesting, but we have other higher priority things to do." Right, and so um, and in time, I was granted the ability to like have some of the people that were already working for me like be told about it first, but then also start contributing to it and kind of gain momentum. About 3 years in, remember it launched after 4 years, about 3 years in, there became this really big decision point. And the decision point became, does Apple actually put significant resources into it? And to launch a language, it's not just about having a compiler. You need to have a book. You need to have Xcode integration. You need to have a debugger. You need to have APIs that actually look nice. It's a much bigger commitment to be able to do this. And so about 3 years in, there was a major series of executive reviews, and that became a whole range of conversations around, should we do this, should we not, like what does this look like, etc. And the pushback, and I think this is actually, by the way, Apple at its best, because Apple is capable of making extremely hard decisions, but it puts those decisions through a rigorous process to actually, the burden is high. And so in this case, like the problems I had to solve were things like, okay, cool, you're going to launch this new language. What if it fragments our developer community in half? What if some people like this, other people like Objective-C, and now we've made our entire community more fragmented, right? Big question. Another question was, okay, well, if Objective-C has problems, why not just fix Objective-C?
That's a very classic kind of argument among industries is always, why not just fix what we already have?
Right.
And so what we did was we said, okay, yes, let's make Objective-C better. And so what we ended up doing is we added modules, Objective-C literals, ARC, reference, memory management to Objective-C, which it didn't have, hilariously, and all these things. And what they were doing is twofold. One is pulling Objective-C forward and making it more productive and better and improving Objective-C in place, but also pulling towards Swift, because we need to talk to Objective-C APIs, so we need modules, or we need to be able to have automatic memory management, and so we needed Objective-C to actually have something rigorous, and things like this, right? A big challenge that I faced was I kept getting these like pushbacks, like from various very senior software leaders, and they would ask these like really elusive questions, like that are not possible to answer, and they were questions like, well, how do we know it's going to be better? Or how do we know that somebody won't like this thing? Or here's this one feature or this one syntax or whatever, and why don't blah, 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 right? Or I don't like the way this feels or looks or whatever, right? And one of the things I realized, and TJ, I think you're getting at this, is that effectively all the software engineers at Apple at that time had grown up and joined Apple because of Objective-C. Like the senior software leaders worked at Next like 15 years ago. And they were there because of Objective-C. And they would ask these questions like, well, Objective-C isn't a problem. Like our entire developer community is Objective-C. The iPhone is successful because of Objective-C. And this amazing, and it is in its own way, it's this amazing combination of dynamism and objects combined with the power and performance of C. And so why are you going to fix this? It ain't broken, right? And what I
Yeah.
realized is that all these people, because they had joined for Objective C, and that's what they knew inside and out, and that's how they had built their careers. Many of them were now in these senior leadership positions. They were not writing code anymore. And so what Swift
Hmm.
represented was a reset of their expertise back to zero. And so, I'm a kind of a dense person. People are maybe not my strong point, but once I realized that, suddenly it became like, don't go engineer brain on this is the way, this is why we're not going to require semicolons or whatever, right? Instead, go into reassuring, like, this is why it's going to be okay. This is why everything will transfer over. We'll keep all the APIs, blah 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 blah. We'll keep everybody, the important thing is the design patterns from the frameworks and the APIs, and like all those come over without change. And I was able to find a way to explain in a way that mapped into the value system, made it so that people, even people much more senior than me, would be heroes in their own journey still and be able to do that.
Hmm.
And that's one of the things that allowed it to get through. Another really big thing that I think allowed Swift to get launched was, people would always ask, very rationally, okay, well, so far a team of like 5 people, 10 people have built this language. Maybe 200 people, most of whom work for me, have seen it now. How do we know it's good? How do we know that we're not gonna, like, we're gonna launch this thing and it's gonna be embarrassing or whatever? And what I told people is, and again, spent a bunch of time going around, and I make this all sound linear, but of course this is very messy and complicated, and in and out and lots of different things. What I realized is that the problem was that Apple, when it launches things, they want to say app developers can be able to use this, and therefore you're protected from incompatibility. And so the breakthrough was when I realized, look, let's just tell people it won't be compatible. Like Swift, you can use it, you can submit to the App Store. We will break your code because we have not gotten a lot of miles on this thing. Our
Hmm.
goal is to make this good, not just nail it down. And once we got through that, then exec leadership was like, oh, well, okay, well, if we're clear about that, then developers can opt out of it and keep writing Objective-C. That's fine. But that way, it's not a one-way door, and that way, we're not walking into a trap if we make a mistake. And it provided a relief valve that allowed it to happen. And so, a lot of Swift, again, as you're saying, like on the human side and on the culture side, on this kind of side, it was these kinds of challenges, which really have nothing to do with compilers or semicolons or the technical stuff, which is also super interesting.
Right.
But was a big part of getting Swift to happen. Another big piece was, um, being able to show how we could go beyond Objective C. And so one of the big pieces was memory safety. And so,
Hmm.
in Objective C, you can't remove pointers and have it still be C or Objective C. Like that was a big thing.
Just
But another
objective.
thing was, yeah, it's just subjective. Yeah. But then the other piece was like, how can we build value add experiences into Xcode and things like this? And so I don't have
Hmm.
a huge amount of love for Xcode practically, but Xcode is very important to Apple, and so that was a big piece of it.
I'm very curious about how you sold people on the ability to say that we're going to have a language in which will break backwards compatibility. Because, I mean, to this day, people are still fighting about Python, right? Like, I mean, I still hear people upset about the 2 to 3 break. And so I can't, like, that just seems like much harder of a sell to be like, you know what? We're going to go out there and we're going to break you. Like, how did you manage to convince anybody that that was a good idea?
Well,
Because
so
the
I think
minus,
that,
minus, and plus, plus, I believe, was your kind of primary example that you gave about breaking Swift.
sure. Yeah, so, well, let me give you again just time frame. Swift is just 10 years old now from its launch. When it's launched in 2014, I think it's still 2024. I lose track sometimes. But Python 2 to 3 took 15 years just for the transition, right? If order of magnitude, something like that, right?
Yeah.
And so
Hmm.
so not only did we make a change in Swift, literally moved the entire Objective C community to a completely different language in less time than Python did 2 to 3, right? So just not. I mean, maybe I'm humble bragging a little bit here, but how is that possible? Well, it's because it's a completely different kind of transition. So in the case of Python 2 to 3, the entire Python program had to move all at once, and so all your packages, all your dependencies, everything. And so if you have um, one little thing that you depend on that can't move or is incompatible, then you're stuck. right? In the case of Objective-C to Swift, there's still a lot of Objective-C and C and C++ and all this other stuff in a modern Swift app. Like a lot of Apple's written a tremendous amount of Swift code for sure, but they still have a lot of Objective-C code in their stack. And so that ability to integrate and migrate and interoperate is so key. And that was, let me tell you, an extremely difficult technical problem, but that really changed the nature of adoption. And so one of the things that allowed Swift to get adopted very quickly is the app developers could take their Objective-C apps that they'd written, sometimes a million lines of code, and then move one class over, right? And so now you have
that's cool. That's really cool.
Yeah.
a whole thing in Objective-C, and I'm going to write some new feature in Swift, right? And so this is where, we take all these lessons to Mojo, and it's the same ideas, right? And so you make it so that you don't have to be monolithically changing everything all at once. You actually work the way the developers work, which is that they want to invest time into things that are cool and shiny and new and important for their business or whatever, not the dusty deck code that's fine.
I just want to ask one last thing, just sort of relating to those sort of people sort of difficulties there. How did you set up, like Apple's huge, first off. So, obviously it's difficult in one way to even have conversations with people across your team regardless, right? Like getting 10 people to agree on something is hard enough, let alone however many engineers work at Apple. But how did you sort of create, I don't know, the culture, or how did Apple create the culture where you could actually have a conversation about getting Swift to go anywhere? Like that's super surprising from my side, just from seeing like, oh, how do you even get people to have a conversation about changing the way things were, like culturally at a tech place in such a big way, right? It's not just like, oh, we're going to switch libraries for logging.
So I think that it's a combination of multiple different things. One is, how should I say this? Apple, again, Apple is like any place has positives and negatives. And when I talk about Apple, I'm talking about Apple 2010, which is very different than Apple today. Okay, and I have been out of Apple for many years, and so I can't speak to Apple today. I'm talking about kind of old Apple and so things are a little bit different. But one of the things that was really true is that there's clear ownership. And so the head of software, this guy named Bertrand Serlet, amazing human. He built a lot of Mac OS 10. He led the team through a lot of changes and did a lot of the core technology within the stack. He happened to be an Objective-C nerd, and he was pushing for things like garbage collection and a bunch of other things to try to modernize the language. And so I got close to him because I was helping drive and work on a lot of these kinds of things. Later, he decided to retire and move on, and his replacement, Craig Federighi, also amazing technical leader, really understood the stuff, came into this, and he had a bunch of Java experience and our JVM platform experience more broadly. And so he brought in a new perspective. And so this idea of having more productive programming languages wasn't just like a complete reject concept at the very top. And so for them, and this is, again, the thing I love about Apple is that at the highest levels, you have very smart, very strategic leaders who are really keyed into what matters for their technology platform. And so the challenge was, there are many challenging conversations at that level for sure, but the bigger challenge is getting consensus and alignment. And now you get the cross-functional people that were leading AppKit or something, and they'd been writing Objective-C for 20 years, and stuff like that. And they had strong opinions, but they didn't own it, but they're important and respected. And so that was much more like the politicking, and that's where things were more complicated. And I don't think there was any magic. It was more about being persistent, about being rational, about being defensive, about hearing them and listening and reacting, about writing docs so that it wasn't just always conversations like, okay, well, if you have this concern, let me actually write it up so that you can scale the conversation. But again, a lot of the thing that was very distinctly Apple is the secrecy thing. And so, again, just to put it in context, Swift launched in 2014. About 250 people at Apple knew about it. Apple had thousands of software developers, thousands and thousands. And, it wasn't just app developers in the audience at WWDC whose heads exploded when Swift launched. It was roughly 90% of software engineers at Apple. so
that's pretty crazy.
That is so crazy.
You dropped a feature as much for internal Apple employees as for the development community at the same time.
And by the way, we have a new language. I love that.
Yeah, so that was an exciting day. We had prepared the team a bit for that, but I didn't think we realized quite how interesting that would be. But you flip it around, right? You talk about decision making,
Mm-hmm.
and there's lots of ways to do it. I'm just going to say this is the way it worked back then. It's way easier to make decisions if you have fewer cooks in the kitchen.
Facts.
Yes.
So having to negotiate with thousands of engineers in an open culture would have made it almost impossible to do anything versus being able to get high level stakeholders who are used to being rational, who, things like this, or the people that you have to bring in and onboard because you have critical cross functional dependencies and things like this. And you can kind of, that's one of the things that makes Apple able to do uh, very discontiguous things. At its best, it can do things that nobody else can do because for example, in the iPhone launch, they completely sequestered the entire software team off from the rest of the company, and they were able to go innovate and build something without having to have a million questions about, well, why not this and why not that, right?
That makes a lot of sense to kind of force that.
Yep.
I've worked in similar sized companies, and one thing that we always did was a informed captain, someone that does farm for dissent, but ultimately just at some point says, okay, this is what we're doing. It doesn't matter what anybody else says. I am the captain. I'm the captain now. I'll just say what
Yeah.
we're gonna do. I do like that approach quite a bit. All right, so something you said, Chris, in the past on I think an interview with Lex, your second one, says progressive disclosure of complexity. I really like this phrase. And how do you apply that to like modern languages, and what does that mean? And which of our current modern languages is the worst at the progressive disclosure of complexity?
Oh, I mean, I'll make fun of it because it's easy to make fun of, but Java is one of the most egregious where it's like, let me show you hello world. It's class foo, public static void main system.out.println square brackets this right. And so like that's the failure, right? It's like, okay, I want to do hello world. Now I have to know what classes are, I have to know what packages are, I need to know what arrays are, I need what is all like what this is that's what not having this is. So Swift, the original goal. So I haven't been involved in Swift development for about. So I left Apple
You can relate
7
this
years
to
ago.
Mojo too. You don't have to relate this
Yeah,
to
yeah. Well,
Swift.
so I'll do both.
Yeah.
And I'll tell you lessons learned from Swift. Right. So Swift, the original idea was factor complexity. So you have really powerful features. They're available and accessible within the language. You don't thrust them in people's face. You make it so that it's simple to get going and then powerful as you dig in. And so progressive disclosure of complexity is this UI paradigm, which is, you can have powerful things that are simple to learn, but then enable power users to discover the power as they progress in their experience instead of thrusting all that complexity into their faces all at once. And the great thing about this, when well done, is that um, it means that it's not just new users, it's also experienced programmers. You have to put less in your head to get things done because normally you don't need the complexity or the power, right?
Mm-hmm.
So that was a big focus of my work on Swift and a big focus of the other language. Massively failed, in my opinion, by the way. So massive lessons learned. Swift has turned into a gigantic, super complicated bag of special cases, special syntax, special stuff, and it's all locally well intentioned. And there are some things that they're trying to do with macros and things like this to try to put into a more rigorous framework. But one of the challenges that Swift ran into, and I'll tell you what we're doing in Mojo, it's very different. But one of the things that Swift ran into is that it scaled the user base really quickly, right? So we launched
Mm-hmm.
it, and a lot of people were ready to get off Objective C, let's just say, right? And so it
Yeah.
found PMF very, very quickly, and so we got a ton of users. It had a lot of internal technical debt because it was built very rapidly, and we didn't expect the adoption to be so quick. And so the whole team was behind. And then instead of fixing the core, what the team did, both when I was there, so partially my fault, but also subsequently, is they started adding all these special cases. There's also some things like Swift UI added result builders and stuff like this. The result builders is a well-intentioned metaprogramming thingy. Get rid of commas to make some code look better on a slide, right? And so a lot of the stuff got added under extreme time pressure to enable a
Mm-hmm.
feature like Swift UI, and there are good aspects of it, but it's one of the reasons that Swift compile times are not great, and there's like a bunch of stuff that kind of feeds into that. as well as just the language gets more and more and more and more and more complicated. Now, Swift's still a beautiful language. It's amazing. It's got a lot of really great things in it, but I can't say that it's a simple language.
Mm-hmm.
And so now you channel forward to Mojo. You say, okay, well, again, 10 years, 15 years later, lessons learned, right? Well, with Mojo, what we're doing is we're both building it in the open from the start so people can use it, provide feedback, build stuff, do this. We're telling people, yes, we're going to not be stable. We're going to optimize and build for the right thing, right?
Mm-hmm.
A lot of what we do within the team is really channel into, okay, well, there's all these things people are asking for. So, for example, right now, Mojo doesn't have classes. Well, why? Well, we know how to do classes. Like, that's like, there's nothing, seriously, can definitely do classes. That's not a big problem. But what we're doing is we're drawing a line and saying, let's focus on this subset and make it really, 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 really good before we move on. And also, a lot of Mojo being a Python family language, Python is really beautiful and really amazing at forcing, for example, almost everything via function call. And so Mojo has lifetimes, has like all these, has async, has like all these things that you need to have in a modern language. All these things are kind of built into the function. And so if you can do function calling right and you get all these abstractions right at the bottom level of the stack, then you can build into and compose onto this extremely quickly. And so my hope is that Mojo remains a much simpler, actually in practice language than Swift is. And now you don't have to factor the complexity; you just don't have the complexity. And so, so we'll see how that goes. I'm very optimistic, but also Mojo has much more powerful metaprogramming facilities. So there's just a ton of special case things like property decorators and stuff like this that got added to Swift that they're just kind of special cases of a more broad metaprogramming feature, and so you could subsume a lot of special cases into one proper subsystem. Anyway, so many lessons learned from that. I mean, Swift is a beautiful thing. Clang, C++, it's a beautiful thing too. But it's also a different epoch of technology. And you talk about Rust. Rust is also the same epoch of technology as Swift, right? And so a lot of the lessons learned from going to Mojo are learned both from Swift and from Rust, and of course from Clang before that, which Swift learned a lot from.
So with Go, it is kind of like extremely simple.
Yeah.
Is that actually simplicity, or is it kind of an illusion of simplicity that you get offloaded into how you have to program? Did you take any lessons from Go and kind of its, like almost dogmatic pursuit of simplicity?
I have a ton of respect for Go. I have a lot less experience with Go than these other ones. I think that Go, one of the lessons learned from Go is that it initially positioned itself as a systems programming language, and it took them a while to learn that they were more of a cloud platform language, and and so some of the decisions made around like garbage collection and things like this and et cetera make sense given a cloud platform language, but in terms of simplicity, I guess the lesson I would learn from Go, and I mean, one of the things I was shocked at with Go is that they actually pulled in a generic system, and it's actually quite good. A lot of people, including like the Java community, they started without generics. They kind of bolted it on. It was never really that great, and so I was really impressed with how they did that. And I guess the lesson that I learned from that is that what the Go community did was they drew the line for a long time, saying we will not have generics. Let's see how it goes without this thing. Let's get a lot of experience. And instead of saying, woohoo, let's have our first generics model, they were very deliberate about it, and they learned a lot. And then when they did it, they didn't just measure twice and cut once. They measured like 200 times and then cut once. And it turned out really good. Right? And so I think that would be the thing I would learn from Go is that you don't, just because everybody's telling you a thing, and this is something I face all the time, like everybody's trying to tell me how to do Mojo or how, like the best way to do a thing, or like, how dare you do this, or like the universal truth of X is Y. And it's like, well, there's no universal truth. There's only trade-off.
I do have some suggestions, but we can save those for later,
Yeah, totally.
One thing I was kind of wondering about, sort of along these lines of this disclosure of complexity and complexity sort of in a language, as someone who actually has people using your languages and projects, unlike many of us and many in the chat, why isn't functional programming popular? That's what I want to know. I love OCaml. Many have been asking me to ask you about OCaml. Why is it that we can't get OCaml to be as popular as, JavaScript or Go or something like this? I'm committed to making it happen, but I'm just wondering what your thoughts are.
I love OCaml. I wrote a scheme interpreter in OCaml a million years
Oh,
ago. Made
yeah,
it properly tail recursive. Like
yes.
OCaml is actually my favorite ML functional language. So
I'm
it's
just gonna
totally a
cut
thing.
it to say OCaml's actually my favorite. I'm getting the clip later. We're putting it on
Yeah,
a t-shirt.
yeah,
OCaml's my favorite. Chris Lattner.
yeah.
We made it.
So also, I'm also a huge fan of Haskell and things like this, but for
Oh,
different reasons. And OCaml, I think, is a much like I like that it's strict. I like that it is much simpler than the Haskell ecosystem
yeah.
and things like that. So the challenge with OCaml and folks at Jane Street and a bunch of other people are working on this, but OCaml still doesn't do threads well. I mean, I think they're getting there. It still has it's very so OCaml and lists and things like this don't work with modern computers very well because everything ends up being boxed and
Mm-hmm.
indirected through pointers. And so these days, unlike 30 years ago, we have multi-level caches. And it turns out, when I was a kid, I was taught algorithms, and it's like, here's the algorithmic complexity of a linked list, and here's the algorithmic complexity of an array. And if you insert into the middle of an array, it's really slow. If you insert in the middle of a linked list, it's really fast, right? That's generally wrong today
Right.
because an array is all next to each other in memory. Linked list is everywhere, and so on a modern computer, if you even just walk a linked list, it'll be 100 times slower than walking an array. And
Yep.
so yeah, it's technically true at massive sizes, but a lot of computer architecture shifted the way you actually have to write code, and things like OCaml and Lisp and things like this are kind of from that previous generation. And so I don't know if it's answering your question. I love OCaml. I think it's amazing. I think that it made pattern matching, for example, which is in now many
Mm-hmm.
languages, but a lot of these good ideas were kind of buried in the functional programming world for a long time. And Swift brought some of that forward, which I think was really fantastic. And
Mm-hmm.
Rust also, and many other more modern languages are rediscovering all this kind of stuff. And so I think it's awesome. But
Yeah. Do you
I'll
think?
reemphasize.
Oh,
I want to reemphasize your question, which is why don't you think functional programming, even just as a concept, catches on? Because everyone who does functional programming, like, starts wearing tie-dye T-shirts and like
oh.
gets converted to the church of functional programming almost immediately. So, like, why hasn't it caught on?
okay, so you want me to piss off your entire community?
Absolutely.
Is that
Like,
No,
that is
just
that.
the
yeah? Okay.
12
Trust us.
Haskell
Okay, yeah.
users.
Yeah.
There's
Yeah,
only
yeah,
12 of them.
because okay, it's because functional programming strictly defined is dumb. Like it
Okay.
doesn't actually make sense. Is that polarizing enough for you?
No, that's good. That's
Um,
great.
More.
so no,
More.
so again, I'm being hyperbolic, right? But here's why, right? So much of computing is about defining mutable state and managing that. Functional programming says, cool, you can do that. And the way you manage mutable state is by making an entire copy of the data structure with the changes in the new copy of the data structure. This is what generally people mean by functional programming, although you can define it in lots of other different ways, right? And so if you say it's purely functional, what that does is that means you have no in-place mutation. Okay. Here's the
Mm-hmm.
problem. Computers, they're all bags of mutable state. And so if you're
Mm-hmm.
saying I'm going to reallocate and copy the entire data structure to make a change somewhere in a tree, well, it's just extremely slow. And so again, back in the day, maybe it was okay. And for many use cases, it's fine, obviously, right? But what Swift did was Swift moved from let's have functional programming to let's have value semantics. And I probably don't want to go into it deeply here, but value semantics are strictly more powerful than that form of functional programming because you get separation and logical composition of behavior like functional programming gives you, but you also get in-place mutation. And so
Mm-hmm.
it's a strictly more powerful model. It is much faster in practice and it's obviously scaled to millions of people and things like this. And so, there are better things than that form of functional programming. Now, it's also super funny because when you say what is functional programming, well, some people say Scala is functional, right? And lots of Scala programmers identify as functional programmers, even though they don't have lack of mutation. They don't. It's not what you would like OCaml or Haskell is that, right? I mean, a Haskell programmer would say that OCaml isn't properly functional because it's not strict. right?
Yeah,
And so
and it has
things like
mutable
this. And
fields,
so
so you can update in
yeah,
place. So it
yeah,
would be no longer
that's right.
functional. Yeah.
Yeah. And so like again, like there's a holy war aspect here, but what when I say functional programming is dumb, what I mean is in practice, like making an entire copy of a data structure change one part of it, like that doesn't actually work well for modern large scale applications. And so that one little piece is that. Now, I love all the people, and so they'll attack me for saying this, but that's okay. I can take it.
I think one I think if we can maybe Prime, if you think it's good too, just like camp out on value semantics for like 5 minutes, because I do think it's really cool, and it goes with some of the things from Mojo too, as well as how Mojo
Right.
sort of does. And then sort of I've seen this popping up in a lot of languages now. Obviously, Rust has a lot of ideas about ownership and borrowing. Mojo has it now as well. I see you guys are working on different stuff with how to manage refs, and are refs going to be transparently accessed? Okay, you got a bunch of stuff going on there. We can talk about those. That's cool. OCaml is adding this as well in a way. They have this oxidizing
Okay.
OCaml project where they're adding like locality and ownership so that they can allocate on the stack instead of the heap. So there's like a
Cool.
sort of an explosion of, I think, this concept across a lot of languages. So maybe, give us your pitch on what is and why value semantics are cool, because I like them as well.
Yeah. So I mean, just let me give you a simple example. You have an array in a purely functional system. If you have an array with 100 elements and you want to set one value into the array, you have to copy 100 elements, or you have to copy at least the array part, which then points to the elements, something like this, right? And so
Mhm.
functional programming done strictly that way destroys O notation, destroys the performance of your program. So then what ends up happening is that if you're building into one of these systems, you start adding tons of complexity to work around it. And so I've built, and maybe you have as well, like lots of really fancy immutable data structures, and there's ways to use trees instead of arrays, and
Mhm.
B trees are like one of the most underappreciated data structure ever. If you want to go there, but it's just a huge amount of complexity. And if you can do in-place mutation because you have the only access to an array, then sure, you totally can directly mutate it, and it actually composes out really well, and it just is better for UX. It's better for performance. It just leads to a better at scale. Programmers couldn't have to know everything and know that there's 5 different ways to have an array. They should just have an array. It makes it way simpler. And so,
Mhm.
um, but now what it requires is it requires either having strong ownership like a Rust or a Mojo has, for example, or being a little bit dynamic, and then requiring building on fancy compiler optimizations. And so Swift is in the being a little bit dynamic and then relying on fancy compiler optimization camp. And so that it works really well for the Swift community, and it's scaled really well, and I'm very happy about that. But a lot of people don't want dynamic effects and stuff like this. And so if you're up for more type system annotations and stuff like that, then you can go with the I know I have unique ownership kind of approach, and that's also cool. One of the things I'd like to achieve in Mojo is a hybrid of both, or you can have a fully dynamic thing for a Python programmer who just wants to write normal code and doesn't care about a little bit of overhead, but then you opt into more strict annotations, and now you can fully control everything, and the embedded systems programmer gets all the overhead out. And if you can blend these two worlds together, then you get something I think is the best of both worlds. And it kind of goes back to that progressive disclosure complexity, right? We want to make it so the Python, most code written by most programmers doesn't actually matter for performance. And so if that's the case, then hack something out, have a lot of fun, go nuts. And then if you want performance, you can layer in type annotations, things like that, and just get it over time. And so this has been done in many different systems over time. It's just never been done in the Python world or I should be careful what I say. Everything's been done in the Python world. So, but I would say it's not been widely used in the Python world because of certain ways that the type annotations work and things like this, which are a little bit goofy in that system.
Yeah, that totally makes sense. I'm kind of wondering along this line of you sort of start with Python as sort of this goal of Mojo. It's a superset of Python eventually, right? And how do you prevent Mojo from becoming Python plus plus, if that's a clear question related to
Yeah.
C and C plus plus?
Yeah, totally. Well, so I think it's, let me flip it around. It is actually a strong goal for Mojo to become a Python++. That is the goal, right? And so people ask me all the
Okay.
time the other side, which is Mojo is the superset of Python. How do you handle the fact that Python will keep changing? Python's not a dead language,
That
right?
was
It
our
keeps
follow-up
evolving.
question.
Yeah, and
You actually
so
got it.
and yeah, and so how do you square with this? And so the analogy I always give is look at C and C++. C was around for decades when C++ came about. C++ was C with classes, and their whole idea was let's add classes and then eventually templates and stuff like this. But it was a different community that got standardized as a different language. And here you're talking about running at committee speed, so it's glacial by today's standards. Um, but what ended up happening is the two languages and the two communities were super aware of each other, and people cohabitated. Programmers cohabitated both community, right? And so what ended up happening is classes of code were built that work in C and C++, and then some people decided to go for C++ because it added value, right? But a lot of people don't know this, but a lot of features went both from C to C++, obviously, but also C++ back to C. So in C, you have the void keyword, for example. That was a C++ invention, but then C adopted. So
I didn't
there's
know that. Yeah.
like, yeah, and so there's a lot of things that happen when you have two communities with different objectives. And the key thing you want is stay true to your objective, stay true to your charter. Again, I'm not anti-Python. We're not trying to kill Python. I think Python's amazing. I love it. But we're trying to solve the C and C++ and CUDA and other parts of the Python ecosystem in one language that can scale, instead of saying, okay, here's the glue layer and here's the actually get stuff done layer. And you have to use two different languages to be productive.
In terms of that, like C, C++ sort of comparison, like C, I mean, maybe it has. I'm not aware of any. Like, basically, never. It feels like breaks backwards compatibility, even maybe to its detriment. But like Python sometimes does. Maybe they're a little more hesitant to do that these days than they used to be. Like, has there been any examples since you started Mojo, or any example you sort of see along the horizon of like Python breaking something, where then you're like, oh, how are we gonna handle this fact that like Python 3.10 does this and 3.12 does this, and we need Mojo to run like in both? Or is it like, oh, you can only run Mojo with 3.12 or something? Like, how is Mojo balancing those?
Yeah, so Guido is the one that's grilled me the most on this, by the way. He's a guy that cares a lot about Python long term and sustainability and compatibility, and he has all the battle scars to share. So there's two places where compatibility with Python matters for Mojo. So right now, today, in Mojo, you can import an arbitrary Python package, and it just works. Okay. And so this allows us to embrace the entire Python ecosystem. You don't have to write FFI or bindings or wrappers, or it just works. The way we do that is we parse and interpret the imported Python package with CPython. We just keep the standard interpreter as it is. And now there's a separate pit of complexity on how do you manage your Python, but we can't fix CPython. CPython is the standard implementation of Python with the interpreter and things like this. Okay. Now, fortunately, there's a ton of people working on CPython. Lots of people trying to make it better, trying to remove the GIL, which will be awesome for Mojo, by the way. There's like a bunch of work going on in Python. We don't have a lot of value to add there, right? There's the huge community of people doing all that kind of stuff. And so, but what we can do is we can use their public APIs, and so we can talk to the Python interpreter through actually stable things, and then Python can go ahead and change itself, and it's fine. It doesn't matter to us at all. Now, things like no GIL and stuff like that are do change some things, and so we have to do minor adaptation in for the big changes. But no GIL is like a 5-year quest or something for Python, and so like we can adapt to things. Like that's fine. Like I said, it takes less than 5 years to build an entire language, so it's So the other side of it, though, is we want to make it really easy to move code from Python into Mojo. And so as Mojo grows into a superset of Python, which it's not right now, it has no classes. That's a pretty big feature hole.
It's
right?
a tough one. No list
Yeah.
comprehensions, which makes us sad. I like writing them. I don't like reading them.
But anyone who likes
Um,
Python says not to write classes. So at least you've picked a good feature not
uh,
to implement right
I don't
away.
know about that. Yeah, that's your okay. You can polarize people, but I actually think classes are pretty cool. But but so anyway, so we're not there yet. But and so because we're not there yet, basically when people move Python code to Mojo, like they have to do a little bit of rewriting, right? They have to change a class into a struct. They have to do some adaptation. But what we've seen in the community is people can move, depending on the kind of code, right? People can move code really rapidly, and it's really easy. And so you have to kind of learn some of the tricks. But once you do that, it doesn't take a lot of work, and a lot of it is because Mojo is it's different in places where it needs to be different, where it's adding value. But otherwise, we stay the same as Python. And so one thing I'll share with you, one thing I generally love Python. Python, I think it's a beautiful language. One thing that I don't super love is the postfix if thing. You say it's like X if
Yeah.
condition else Y. Like I don't
Right.
just square. Honestly, I don't love that. But guess what? That's what Python does, and so that's what Mojo does.
Right.
Let's not debate it. That's the thing, right? And so
Yeah.
because of that, right, what it means is that if you're experienced with Python, whether you love all the pieces or not, like it makes it much easier to bring over. And list comprehension, yeah, we'll do that. We just haven't gotten around to it either.
Yeah.
Now, when you grow into a full superset, right, that's I think what you're asking about as well. And then you say, okay, well now I'm moving things from Python 3.85 to whatever, and how does that handle and stuff like this. And so for that we can have the idea, and this is a lesson learned from Swift, by the way, is to have migrator tools. And so it's not that the code magically works. Like in Mojo, we're taking a new keyword, right? You can decide what the new keyword is, but we want to be able to do that. That's very important to make the language consistent and coherent and things like this. And so we don't want to be ashamed of doing that. We want to do the right thing for Mojo. And so what we can do is we make it so that, okay, there's a mechanical tool that you run that then just escapes the keyword, adds an underscore to it or something, right, if you're using it. And so we can make it super easy to mechanically import. And that tool can then have a version flag.
Cool. That makes sense.
And also, going back to Swift, right, Swift was incompatible with itself for multiple years. And so as it came out with new features and it broke code, what we did was we provided a migrator. The migrator parsed old Swift code and upgrade it. And it did a, I don't know, 90% job, not 100% job, but it was still very useful and it helped the community move over. And so this is also the way I look at eventually being syntax compatible with Python is, we technically will not be a superset because we take a new keyword or something. But guess what? C++ is technically not a superset of C either.
Correct.
It takes new keywords. And so it's fine. Like we as a community can manage that. It's not that big of a deal.
Yeah.
Kind of switching gears here. You obviously have created a lot of really large projects, and these aren't just weekend projects; they are multi-year projects, and they're still going on today. And you've done a lot. You've stated that you learn by building, and so you said, how hard is a C compiler? So you just started working on it in nights and weekends and all that. And there's a lot of questions here that I'm sure people would love to ask, which is like, how do you choose your side projects? How do you stay motivated to complete these? But before you answer any of those, could you just kind of give us like, how do you even manage your time exploring these new concepts versus working on the things that are already huge to begin with, such as like, how do you switch from LLVM to the next thing? How do you switch from Swift to the next thing without just getting bogged down with all of these like requests for new things or your insights into things?
So I thought you were gonna be nice to me, and now you're pointing out that I have like an attention problem, and I can't stay working on something for more than 8 years.
Yeah,
Attention is all you need. Attention is all you need.
There you go. Well, in all seriousness, so I'm unusual in many ways. One of the ways that I'm unusual is that I love to build things, understand them, but I also do get along with humans sometimes, and I try hard, and I'm learning, and I'm getting better as I grow. And so, take Swift for example, right? In the case of Swift, it was nights and weekends project for a year and a half. At that time, I was managing a team of 40 people or something. I don't remember exactly with the debugger, which is itself a team, the Clang stuff with Objective-C and C++ and all that kind of stuff. And we built an entire code generator for Apple's GPUs to make it so that Apple could insource its hardware design. And so there's tons of stuff going on within my team. Maybe it was bigger, but I don't remember. But and so like I had a day job, but each of those projects, had gone from being something that got catalyzed, something that got built out, something that got proved and validated, to now there's a whole team around it that was building it, and they're doing it better than I was. Right? And so me trying to be an engineer on the team as a pointy hair boss, as a manager, as a whatever, it's these amazing engineers' full-time job. Like, I don't add a lot of value. The value I was adding is maybe architect, maybe as helping with problem solving, pointing them the right way, classical manager or tech lead manager type of roles. And me as a technologist, like, I like to build things, like you were talking about. And so that means I then start looking around and saying, okay, well, what's the next logical thing to work on? And so that's where, again, Clang or Swift or things like this, it was more about, there's no ambition for it to become anything big. It was more about just build some stuff, see where it goes. When Swift, I was working on it for a year and a half. It wasn't because I want to do world domination. It's more about, okay, well, let's just see what there is to do here. And I have some ideas. Let's prototype some stuff. Let's have some fun and build it. It's very fast. When you only have something in your head, you can spin very quickly and you don't have to have meetings. And so it's very fun in a different way. But then, to your point, what happens is then you want to get beyond what you can do in your spare time. It becomes more important. You understand it. You can explain it. Then you start bringing more people. There becomes a team. Then there becomes a tech lead or a manager. And then at that point, I can grow out of it and do this. One of the things I've discovered across the years, which is not obvious, is that because I've kind of been in this role of like invention, creation, innovation for so long, it's super funny. For example, I was working with a team at Google. We're building high performance runtime for machine learning stuff, and just getting within the Google confines, the approval, air quotes, which was massively not defined, of like consensus of, yes, we should build a new runtime for TensorFlow. Like, achieving that was this massive heroic effort, just political and just gigantic mess. We got consensus to do this, and then I had a team, and it's like, okay, team, go. And it's like, space is clear. Let's go build this thing. It's really important. Go. Right. And I was doing a bunch of other things at the time. I'm like, hey, go. Right. And nobody could do anything. And what I realized is that, again, brilliant engineers, right? This is, again, Google and working on machine learning infrastructure and high performance accelerators and TPUs and stuff like this. What I'd realized over time is that these amazing engineers had only ever worked on a mature project. They'd only added a feature or fixed a bug, or they jumped into a big code base, particularly at Google. The strong engineers, the experienced engineers, like, their major feature is that they can absorb a huge amount of complexity, fit it in their head, and then figure out the way to logically hill climb the thing that they have. And outside of college, very few people have the opportunity to build something from scratch. And so you're sitting there and you're saying, okay, in front of us is this, I'm standing on the edge of a cliff looking off into space, and to me, I'm like, oh, I can see a castle over there, and I can see this thing over here, and I can see how this all goes together. And for other people, it's just terrifying because they didn't know where to start. And so there's all these, again, across the years, because, getting more experience with things, there's these patterns. And what I've seen is that there's folks that will start from space and just be paralyzed. There'll be other folks that just say, like, oh, okay, well, I'm going to build a new thing. Well, there's this old thing I've already worked on. I know that it works. Let's just re-implement that. And so the thing I like to do is I like to say, okay, well, we're going to build a new high performance machine learning runtime or a language or a whatever. The starting point for me is not just go hack up the thing that I thought before. It's go study all of the things. When I was working on Swift, it was great. It was kind of in parallel with Gradle and working on Rust and things like this. But also there's a bunch of other languages that were really cool, both modern and also like OCaml, for example, Yestafan and Haskell and things like this, but also really older ones as well, like some of the fundamental ones like CLU and things like this that many people don't remember. And so going and studying and looking at like Dart, for example, right? It's a very specific domain that it wants to live in, and it makes a bunch of decisions. It's very specific to the problems it's trying to solve, but the way it did Unicode escape and strings was really cool. And so we said, yoink, I'm going to take that and put that into Swift, and that's the best way to do it. Way better than what C did or whatever it is. And so my approach is generally do that research, do that survey, and build a picture, build what that castle looks like out in space, so I know what I'm trying to get to, and then iterate and refine it over time. And so I don't even remember what your question is anymore, but
That's
this
okay.
is how
I
I
have a
like to
good
build
follow up,
games.
anyways. So
Yeah, cool.
I think this is like one of the biggest weakness of all engineers is not knowing when to quit, which is either they quit too
Okay.
soon or they quit too late. How do you know what, like staying up for a year and a half on nights and weekends programming Swift? When did you know, like, oh, I shouldn't quit this, or how do you know, oh, I should quit this and pursue something different? Like, what is that kind of thought process you have for
Hmm.
quitting?
Well, let me give you a modern example in modular. Right? So I assume most of your folks don't know what modular is about, and so I'll give you some context, right? So uh, context here is that AI is exploding, super annoying in lots of different ways because there's lots of
Yeah,
buzz and stupidity and stuff like this. Right? But the systems level, the foundational infrastructure underneath it is very profound, very important. And AI, despite some of the annoying stuff, is also really important. And there are really important use cases at scale for businesses. And there's a big there there. Okay. Now the problem with it is that the technology platform this is all running on is a gigantic freaking mess. And there's CUDA, for example. There's like, when training, there's still things like MPI, and there's like all this stuff that is just this gigantic nightmare of technologies, and it's never been really thought out. And so one of the things I realized is I actually gave a talk several years ago at this Ask Plus conference, and if you want, you can find a link. It was 2021. I gave a talk about, it's the golden age of compilers because there's all this hardware, and what we need to do is we need to build a unifying theory that allows us to innovate in hardware and be able to get all this stuff, get software developers to be able to build on a common platform so that you can then scale across all of the different kinds of hardware, because most of us, all software engineers, don't want to rewrite our entire application every time the thing changes, right? The hardware changes, right? We want this. And also, by the way, the hardware people don't want to reinvent an entire software stack every time they want to come out with a new chip. Right? Basic observation. And so when we started modular, we said, how do we solve that problem? And so here's the ridiculousness, because you're giving me a hard time. You're saying, Chris, you do these possible things, right? Um, Actually, push this on stack. Like, and give you an example. It's like when I joined Apple out of school to work on LLVM. Like within the first month, the very senior lead of the GCC team comes up to me and says, "Chris, why are you working on this LLVM thing? It's an academic research project. Hundreds of people have been working on GCC for decades. Like, you're doomed to failure. Why are you even bothering? Just work on GCC, right?" And when working on Swift, it's like languages never work, right? Again, it's phrased generally more passive aggressively than this, but new languages never work. Nobody ever adopts them. Languages are too expensive to build, blah, blah, blah. You're doomed to failure. And so I've been told I'm doomed to failure so many times. I'm pretty used to it. Twitter only amplifies it and makes it more frequent, but it's all good. And so with modular, you go into this and you say, well, what is our objective? Our objective is not just to build a unifying platform for this next generation heterogeneous compute, CPUs, GPUs, accelerators, all these new things that are so important to the world, but it's to beat the state of the art of the hardware vendors on their own chips. Well, how do you do that? You talk about Rust. How can you be faster than Rust? Like, how can you beat Intel, who's been building software for their chips for 20 years? They know their chips better than anybody else. How can you beat Intel on their own chips, right? And so what we started out with the company is we said, okay, well, let's go. We have a hypothesis that we can do this. And how's the hypothesis shaped? Well, built a new compiler framework called MLIR, which is kind of like, you can think of it as like a successor to LLVM. It was really cool, really profound. Nobody understood how it worked. There's a bunch of new algorithms. There's a bunch of ways to be able to generate code. When you get into this accelerator space and high performance compute, even on CPUs, you have to use the hardware blocks. Like, all these things have matrix multiplication operations now, and like all this stuff is built into even CPUs, but definitely accelerators. Right. So the entire game, which, by the way, none of Swift or Rust or any of these languages even attempt to solve, they can barely do SIMD. But the entire game is, how do you actually utilize a modern computer? And now you're multi-core. On servers, you have multiple sockets, and so you have what's called NUMA. So the memory access patterns are very different depending on where you're doing your accesses from. And so nothing in this world has been designed for this kind of computer. And you look at, again, I'm not anti-Intel or anything, but you look at general high-performance software, and it was written for chips 20 years ago. And so what we did coming back to your point of how do you know when to quit, is we said, okay, let's build some really crazy ass high tech stuff that nobody else in the world knows how to do. Like very different architecturally. Yes, you need a high performance asynchronous runtime on the bottom. Yes, you need an entirely new thread pool. You need an entirely new way to program SIMD. You need an entirely new way to generate code and do automatic what's called kernel fusion, so you get rid of memory traffic entirely and things like this. Let's build this really fancy compiler thing in a way that we could show that we could generate matrix multiplications that run faster than Intel MKL on Intel chips. And we built all that kind of stuff out. And like good scientists, and you want to validate the hypothesis. And so we built this really fancy compiler stuff that nobody else has. And then we showed and we proved to ourselves that, yes, we could beat Intel's best drag racing on their chips, even though they have thousands of like insanely amazing people writing assembly code. And that what we proved is that the generality of a compiler beats humans special casing individual point solutions, because humans can't scale, the compiler can scale. And this is, again, a very different generation of technology than something like LLVM, right? And so the problem then we had was we got to the end of, this was the end of 2022, and we said, cool, we have this really fancy compiler stuff, we can do this, we can generate code. Problem is that there's like 3 people in the world that can possibly understand this, because you have to be able to understand all of the compiler internals and all of this crazy stuff, and we validated that, yes, we can do it, so let's not stop. But then we said, well, how are we now going to program this stuff? And then we said, well, we need syntax.
Mm-hmm.
And then we went shopping for syntax, and then we decided Python, and then ... that's what Mojo is. Right? And so
Yeah,
Mojo's not a, like, let's go build a language for fun. Mojo was a solution to a series of equations of, we have this really fancy compiler stuff built for next generation accelerators and GPUs and all this kind of stuff. Now we need syntax, and Python is the obvious syntax, but we can't use the Python implementation or the Swift implementation or any of these compilers because they don't have any of the right guts inside of them. And so that's the world that Mojo is coming out of.
One of the interesting things about Mojo, I think this is probably the last one before we move, Prime, is my understanding is Mojo is like effectively just an AST4 MLIR, right? That's what you've said before. There's sort of like, it's a direct like link to MLIR.
That is true, but that really that is absolutely true, and there's an incredibly valuable thing about that, which I expect most folks won't grok. But many of today's systems, whether it be on your desk, like an Apple Silicon thingy, but also these very fancy data center accelerator things, they're very different computers, and so the way you need to program them is very different. And MLIR is the right way to do that. But the problem with MLIR, and this is another thing that annoys me to no end, is that MLIR, which is now an LLVM project, so it's part of the LLVM umbrella, it has all this super academic, crazy stuff in the project, and we use almost none of that. We don't use the MLIR dialects at all, and so not only are we the only language that front ends to MLIR, which is itself a very important thing when talking to all the ASICs and stuff like this, but we've rebuilt the entire compiler stack from scratch. And so this is, again, when you say, how can you be faster than X? It's like, well, we have a completely different stack we've built from scratch. It is actually new technology, and I think that's where people are, I mean, maybe it's part of the success of LLVM is that everybody just built on top of LLVM, and they're all the same. And so people are like, oh, okay, well, languages are all the same if there's zero cost abstractions. And it's like, well, that's true if you're all using the same code generator, but if you're doing something new, then it's not all the same. So
that's a great answer.
Yeah,
I now submit that Mojo can be faster than Rust, now that I know that you're swapping out what car you're driving.
Yeah. And again, LLVM is a good thing, but LLVM is 20 plus years old, right? I mean, it's a good thing, and I mean, I'll just speak for myself. I've learned so many lessons, and very proud of what it's been able to do and its contribution to the world. But it's not perfect by any stretch of the imagination. I know the problems better than anybody. In fact, if you look at the LLVM developer meeting last fall, we gave a talk about Mojo, and we explained it's like we use LLVM the good parts, not the broader LLVM system.
Well, thank you very much, Chris, for joining us for the remainder of the time, because we have you just for a little bit longer. I know you got something here in about 20 or about, what is that, 19 minutes. We're going to switch over to the Discord. I'll stop the stream and then I'll walk you through exactly what to do. and we'll field a couple questions from the top shelf for those that are on the top shelf. That would be tier 2, tier 3s from Twitch. You get to go over. And then anyone that has a sufficiently neurotic question, I will then ask Chris that question, and we'll see how it goes. All right. Hey, thank you very much for coming on. Really appreciate it. By the way, it absolutely just a treat to talk to you, and just the things you've accomplished are truly an inspiration to a lot of people in the chat. A lot of people said you've made, like, you were an inspiration for part of me programming and all that. So thank you for everything you do.
That's amazing. Yeah, also, I mean, I'm very happy that the things, my nerdy little projects are interesting and useful for people. And so it's amazing.
They're not just useful. I mean, we wouldn't have a lot of our modern languages without it. So I love Zig, and Zig is currently on LLVM. So I'm sure, I don't even know if it would be possible to have Zig without that in its current state. So thank you.
I also love Zig. So,
man, I wanted to ask you so many questions about Zig. Oh, man.
Yeah. Well, a lot of Zig is in Mojo, including the entire metaprogramming system. So, I mean, that's a huge
That's got
inspiration.
comp time.
Again,
we'll talk about it in the top shelf.
Okay, let's go to the top
Stop
shelf.
getting distracted.
So this is again, people are not used to the fact that progress is being made all the time, and so you have to learn from it.
All right, awesome. All right, hey everybody, thank you for joining. We're off to the Discord.